Today we're going to talk about the 4 general reaction types that all chemical reactions can be sorted into. The first one we're going to talk about is synthesis. It's also sometimes called composition, so we're going to include that, composition. Synthesis is exactly what it sounds like. When you synthesize something, you make something. In this case, you're going to be making something bigger. So you're going to have smaller pieces, and in the end, you're going to make a larger compound or molecule. So let me give you an actual chemical reaction that'll show you a synthesis reaction. This is one that's actually in Table I. This will also give us an opportunity to review what the letters in the parentheses mean. The G means that it's a gas, and L means that it's a liquid. If you see an S, it's solid. If you see AQ, it's dissolved in water. So this is a synthesis reaction because we have 2 small molecules here. We have H2 and O2, and we're making one larger molecule, H2O, or water. So a general reaction might be A, like the H2, plus B yields some larger molecule, C. Sometimes thinking of it in generalities helps too. So you have 2 smaller reactants and you make a larger product. The next one, decomposition, is actually the opposite of synthesis. This is when you're taking something big and you're breaking it into smaller pieces. And the name kind of implies that too, decomposition. When something decomposes, it's broken down over time. An example might be, this is actually methanol, the simplest alcohol, not one you'd ever want to ingest. Makes you blind and eventually kills you. But you can actually see here we have a larger molecule, and it's broken down into smaller ones. So a general formula for that might be, here's our large molecule A, and it's being broken down into 2 smaller ones, B and C. So you have a single reactant, and it's broken down into 2 smaller products. All right, next one, single replacement. This is a little more complicated. One of my colleagues likes to say it's 1 in, 1 out. Might make more sense once you've seen the reaction. So we have here a single element, potassium, and it's going to react with a compound. This is actually water. We've just written it a little differently. You're going to see it like that on occasion during the school year. And what's going to happen is this potassium is going to switch places with this H. That's what's going to happen on the other side. So now K is with OH. So you can see where that K went. And then the H's that are left over are going to be by themselves. I like to, of course, humanize or personify a lot of my elements and my reactions. So I like to look at this and say, okay, well, we had this person who was single, and here we have a couple. We have H dating OH. And then what happens is OH is noticing K. K's pretty good looking. And OH dumps H to be with K. Now this is the new couple, and H is now crying in the hallway while her friends console her. So when we say 1 in, 1 out, there's a different single element, that's the 1 in, and a different single element, when you come back out of the reaction. So if we were to write a general formula for this, we have some element A by itself, and then B and C are together in a compound. And after the reaction, now A is with C, and B is by itself. Now, this can actually get more complicated, and we're going to get into this more when we do some examples. But in order to predict whether or not this will happen spontaneously, we're going to use table J. So if you look down at the bottom here, there's a spot for us to fill in what table J is for. Table J is used to predict spontaneous or not. We're going to use this table a lot throughout the course of the year. So I'll actually pull it out when we get to the back side and do some examples. All right, let's go back and talk about double replacement. Double replacement is when we're going to be swapping partners. It's not unlike single replacement. The difference is that they were both in a couple to start with. We'll do an example to make it make more sense. So we have potassium in a compound with iodine. We're going to put this in water. That's what AQ means. And we have lead in a compound with nitrate. And again, we're going to put this in water. A lot of times lead doesn't dissolve, but it does with nitrate. So now what's going to happen is we have this metal and this metal, and they're going to switch places in the compounds. So we're going to come up with our products. Now K is going to be with NO3. I don't actually need the parentheses because K, when we look up its oxidation number, is +1. NO3 I would have to look up in table E, it's -1. So all I did here was put my metal from this one with my, well, non-metals, plural, my polyatomic ion from this one. And now I'm going to do the same thing with the lead. So lead is now going to be with iodine. We're going to run into a little problem here with lead, though. Let me pull out my periodic table. Lead is over here. It's pretty heavy metal, but what you're seeing here is it has multiple oxidation numbers. Where potassium, we knew it had to be +1. Lead is a little more complicated. What I need you to do is assume, unless we tell you otherwise, that the oxidation number of lead as the product is the same as it is as the reactant. So we need to figure out what lead is when it's with nitrate. So now we need, I know that's a lot of flipping around, we need our table E. So now we have our table E. We just need to find nitrate. Not here, not here, not here. Oh, here it is. And its oxidation number is minus, and we assume a 1. So let me get that out of the way. So nitrate is -1. And since there are 2 of them, that means that it totals -2 for the negative half of my compound. So in order for the whole thing to total 0, that means that lead must be +2. So we're going to go ahead and assume that lead is +2 here, and we look up iodine. Iodine right here is -1, as the halogens often are, -1. And now they don't cancel out, so we're going to swap and drop. Don't bring the sign though, and I'm not going to draw the 1 on the lead because chemists don't typically. Now there's one more thing that we should probably do now that we have our 2 products, and that is see if one of them is a precipitate or not. In order to figure that out, we use another table, table F, and table F we use to determine solubility. Solubility is just whether or not it will dissolve in water. All of this is happening in water. So we want to know, will this be soluble? Will this be soluble? So we're going to have to use table F to determine that. Now, table F is not an easy table to use, so we're going to spend a little more time on that. So let's go ahead and write a general formula for double replacement. We have compound A, B, so that'd be like K bonded to I. And we have C bonded to D. And then on the other side, and you have to be really careful with this, a metal can only replace a metal. So those two are going to switch places. Some of my students in the past have said, oh, it's kind of like foil. A is going to be with D, and C is going to be with B. So it's the outside and the inside. Be careful, though, when you write your formulas on the other side, the metal always comes first in the compound. Notice I have K first in this compound, lead first in this compound. So be really careful with that. So we have A with D, and we have C with B. The element that came first in the compound on this side needs to come first in the compound on this side. It doesn't matter if you said CB plus AD. Doesn't matter which compound you put first on the product side. So let's first talk about our different chemical reactions, see if we can identify some of these before we complicate it with spontaneous and whether or not we have a precipitate. So our first reaction here, we have one reactant and we have multiple products. This is an example of decomposition. I'm going to, of course, abbreviate this. D is going to be decomposition. Let's look at the next one here. We have copper chloride, so we have a compound, and we have a single element here. And on the other side, now zinc chloride and copper. So we have one single one coming in and a different single one coming out. So this is single replacement, and I'm going to abbreviate that SR, single replacement. Next one, we have water, so we have one compound, and we have multiple products here. We have hydrogen and oxygen. This is a reaction we're going to do during the school year. So that one, we started with one big thing and we made some smaller, so again, that's decomposition. Next one, we have potassium chromate and iron chloride. And on the other side now, potassium is with chlorine, so these two ended up together, and then iron with chromate, so iron and chromate ended up together, so that's going to be double replacement. We joke every year, we tend to have this near the Christmas formal, the holly hop, and it's kind of like what sometimes happens with some friends at the holly hop. One person asks another to go to the dance together, and then the friend asks the other friend to go to the dance together, but by the end of the dance, they've actually switched partners, and the couples have switched. So look for that. If you haven't been to the holly hop yet this year, look for that. It might just happen. Next one, we have carbon with bromine, and we have chlorine. It doesn't matter that there's a subscript there. That's still just chlorine all by itself. On the other side, we have carbon with chlorine, and then bromine by itself. So we had chlorine by itself here and bromine by itself here. So we had one come in and a different one come out. So this is single replacement. Next we have one large compound, and then in our products we have two smaller things. Again, that's decomposition. We haven't seen a synthesis yet. Silver nitrate, sodium chloride. So we have two couples, and on the other side we have silver now with chlorine and sodium with nitrate. So that is double replacement. That's the hollyhop reaction. Over here we have two small pieces making something larger. So we finally got our synthesis. I'm going to abbreviate that with S. Now I want you to try the next two and you'll probably be asked to answer one or both in Edpuzzle. Great. Hopefully now you can identify reaction types given the reaction. You may at some point be expected to come up with the products of double replacement reactions, but for now, let's go ahead and use Table J to predict if these different reactions will occur spontaneously. So let's get Table J out. Here is Table J. One of my colleagues calls it the list of who's hot and who's not. Because essentially what's happening over here is nitrate is dating aluminum, and tin is standing over there, and if nitrate thinks that tin is better looking, aluminum's going to get dumped and nitrate will be dating tin now. What we're going to do is determine whether or not tin is better looking. I don't personally think that that's the only way to evaluate a partner. I kind of think humor is important, but that's just me. And we're going to look at Table J. Table J is where they're already ranked, from the hottest to the not as hot, which is kind of funny because this is actually gold. But copper, silver, and gold are the least reactive metals, which actually makes them pretty valuable in applications like making jewelry and things like that, because they don't oxidize quite as easily as some of the others. Since we have the one that's alone is a metal, we know we need to compare it to the metal here. If you look at Table J, we have a metal side and we have a non-metal side. Non-metal side's pretty short, it's just the halogens. But in order to decide which side of the table you're going to use, you look at whatever element is alone. Since tin is a metal, we're going to compare that to aluminum. By the way, in case you've forgotten, tin is actually Sn. I know it's weird, but some of our elements do that. Tungsten is W. So now we're going to use Table J to figure out if nitrate would dump aluminum to be with tin. Okay, so let's find aluminum. Here's aluminum. It's about halfway up the chart, which means it's pretty good looking. And we're going to look for tin. Oh, tin is way down here. Since aluminum is better looking, nitrate is not going to dump them. And then the explain why or why not. The reason why nitrate wouldn't dump aluminum is technically because aluminum is more reactive. The compound you end up with after the reaction always has to include the more reactive element. Since it's already with the more reactive element, it's not going to react. All right, next one. We have silver by itself. So again, we're going to be comparing metals. We have silver and gold. You may need to look this up in Table S, but silver is Ag, gold is Au. So we're comparing silver and gold. They're down at the bottom. They're not very reactive. We have silver here and gold here. So silver is actually better looking, and as a result, chlorine is going to dump gold in order to be with silver. So the reaction will occur spontaneously, and the reason why is silver is more reactive. Next one. This time we have fluorine. Fluorine is a nonmetal, so that means since that's the one that's alone, we're going to compare it with the nonmetal in the compound. And you'll actually be reminded of that when you go to use the table, because you're not going to find fluorine on the same side as calcium, so you can't compare them. That's like comparing apples and oranges. So we're going to compare fluorine and iodine. When will calcium dump iodine to be with fluorine? Absolutely. Fluorine is much higher than iodine. It's actually the most reactive nonmetal. So calcium is going to react by dumping iodine to be with fluorine. So the answer is yes, and our reason why is fluorine is more reactive. We'll do one more together, and the rest I'm going to have you do on your own. I'm going to hold off on reviewing Table F until the next set of notes because it is rather complicated. I was hoping to do it with these notes, but I don't want them to get so long that you lose track of what you've learned. All right, next one we have magnesium by itself, which is a metal. So we're going to compare that to the metal here. Magnesium is Mg, strontium is Sr. So let's look. We have Mg here. Sr is higher. Sr is the more attractive. So acetate is not going to dump strontium, so nothing's going to happen. There will be no reaction. Acetate's already with the better looking one. And the reason why is strontium is actually the more reactive. So go ahead and try those last 5, and you may be asked about one or more of those in Ed Puzzle. So go ahead and check your answers against mine. Hopefully now you know how to use Table J in order to predict if a reaction will occur spontaneously, and also that you can identify a reaction type given the reaction.